Okay, so good afternoon, ladies and gentlemen. Today I have a big pleasure to welcome here Maria Neuss-Radu. You know her very well, but anyway, let me say that she did her PhD in a long time ago in Cluj.
No, my studies
My
I did
study
in
was
Cluj.
in Cluj, and then she did PhD in Heidelberg. And then after some while, she moved to Erlangen when she's professor position got, and she's working in important part, which means, let's say, homogenization. And today we will have lecture about effective interface law for fluid flow and transport through reactive porous membranes. Please.
Yes, so thank you very much, Sharka, for the kind introduction and also for the invitation to come here. So it's a big pleasure and a big honor to speak here and in Prague and in this famous university and with this very nice and precious colleagues which we have here. So I'm working, as Sharka said, in the derivation of effective models by the methods of periodic homogenization. And today I will present you a coupled problem which includes fluid flow, transport, reactions, diffusion through porous membranes. I will say what I mean by this. But first, let me say that the results which I present today are jointly with Marcus Gahn, who is also here in the audience, and my colleague from Heidelberg University. And the results which I present are some of them are new, but also many of them are based on a series of results which we have developed during the years now. Okay, so let's go into the subject. I will start with a short motivation. So you see, I will talk about membranes. What is a membrane? It's a thin layer which usually separates two bulk domains. And these such thin layers occur in many applications from material science, from geoscience, from biosciences. And our motivation is mainly from biology, where such thin layers, processes to such thin layers occur when you have, for example, in the blood vessel, you have the endothelial layer which separates the blood from the tissue. You have it in the lungs, the so-called blood-air barrier, which separates the air space from the blood in the blood vessels. Then you have in the gastrointestinal wall. You also have such thin layers lining our organs. So, of course, it's very difficult to model such complex biological systems. Yes, this is not possible nowadays. So people made some very important progress on the experimental side, where they tried to mimic the real organs by some experimental devices, so-called organs on a chip. And you see here such an organ on a chip which mimics the lung, the blood-air barrier in the lung, and there you have a thin layer which consists actually of two layers of cells. You have the endothelial cells which are in the blood vessel, and then you have the epithelial cells which are on the side of the alveoles, and then this layer separates the inside of the alveoles and the inside of the blood vessel, and the exchange of gases of O2 and CO2 occurs along this thin layer. And but it's not just, as I said, such organs on a chip you find in mimicking many organs of the organism, and in many of these experiments, you see flow, you see diffusion, advection, chemical reactions, exchange of substances between compartments, and I want to try to give you a model which combines and couples all this type of processes. Okay, now let's first formulate the geometry. So what we now, from the mathematical point of view, we have some geometry which consists of a domain, which consists of two bulk domains, yes, and then they are separated by such a membrane, which has two, let's say, in the bulk domains, we consider we have fluid flow and transport and diffusion in this fluid part, and then we have this membrane or this thin layer with this porous structure, where we have this blue part. And this we imagine is a solid part. For example, it could be it could model this cells which you see here, and between these cells you have the extracellular space. So again, fluid. Yes. Now here it is very simplified. The cells are presented like such bars because you cannot draw more complicated things, yes? And in between, so these bars are a solid domain, and in between we have this porous part, which is connected to the porous, to the fluid part in the bulk domains. And now our full domain is the domain omega, which is now an interface sigma, which is an interval AB in R2, and times minus HH. So this is the whole domain here. It consists then of the bulk domains omega epsilon plus and omega epsilon minus. Why epsilon? Because epsilon is this what gives us first the thickness of this layer and also the periodicity of this layer, because I said this has a complex microscopic structure, and this is periodic structure, and it is obtained by taking such a standard cell, periodicity cell, and then we scale it by epsilon, and then repeat it all over this layer here, and then in this way we obtain such a microscopic structure which forms the layer omega epsilon m, which is now the full layer. Omega epsilon m is the full layer having thickness 2 epsilon. And then it is bounded from above and from below by the surface S epsilon plus and S epsilon minus, yes. And then we have this layer has two parts. We have this blue part, which is the solid layer, the solid phase, and it is denoted by omega epsilon S. And here, and omega epsilon ms, and then we have in between these bars, we have the fluid part, and this we denote by omega epsilon mf. And this both domains here in the thin layer are separated by an interface, which we denote by gamma epsilon. Okay. Now, what we also have next notation, which we should keep in mind if we manage, is we are of course interested in stuff which is transported in these bulk domains and is interchanged or exchanged through this layer, and therefore for the fluid domain we are interested to have a domain which connects all fluid parts. So we have the upper layer omega epsilon f. Omega epsilon plus, omega epsilon minus, and omega epsilon f, the fluid part in the layer. This is the whole part occupied by fluid, which we denote by omega epsilon f. Yes, so omega epsilon f is everything but the blue part. And the blue part is then our omega epsilon ms. So we have this fluid part, and we have this bars which model our solid part. Okay, and now what could happen? It could happen that that here in this, you see here in the standard cell, we could have another cylinder here, which touches the upper and the lower part of the standard cell. We in this talk, I avoid this. I say that our solid part here is can touch the lateral parts of the cube here, but not the upper and the lower. It's not a cube of this cuboid, yes, yeah, what to call it. Three-dimensional interval, but this blue part should not touch the upper and the lower part. That means this structure will not touch the bulk domains. Yes, I hope this is clear. So this should be clear. If this structure touches if we would have here another cylinder which touches the upper and the lower part, then we will get in the limit different models. Okay, good. Now. Here in this standard periodicity cell, again we have some notation. So the whole standard periodicity cell we denote by Z. The blue part, which is the solid part, we denote by ZS, and the surrounding the fluid part in the starter cell, we denote by ZF. Yeah. Okay. Now, in this domain, domain which we call the microscopic domain, we formulate the following problem, which we call the microscopic model. So first, we formulate we have fluid flow, and this is modeled by the Stokes equations. And you see we have V epsilon plus, V epsilon minus, and V epsilon m. This is the velocity in every of these three compartments where we have the fluid. And in the bulk compartments, you have the Stokes flow with the source term F epsilon plus or F epsilon minus, and omega epsilon plus or epsilon minus. And in the membrane domain, so in the fluid part, in the porous part of the membrane, we have again a Stokes equation for the velocity V epsilon m and for the pressure P epsilon m, which is now scaled. So we have the viscosity scaled by epsilon, and in front of the pressure we have scaling 1 over epsilon. Okay, then we have here the incompressibility condition, and we have now boundary conditions, and we have to consider boundary condition at the outer boundary, and then we have at this interface between the layer and the bulk domains. Also, there we have to put some transmission conditions. Yes. Okay. Now. We have several boundaries. So we have this Neumann boundary where we impose that the normal stress is 0. The Neumann boundary is upper and the lower part of our domain omega. Then we have the lateral boundary. At the lateral boundary, we impose periodic boundary conditions because to simplify a bit some parts of the analysis. This is not important, but simplifies a bit the technical part. And then we have this interface. This interface gamma epsilon between the blue and the white part. Yes, and on this interface gamma epsilon, we will then have the continuity of the velocity and the continuity of the normal stresses. Okay, good. Now let's continue with our model. So in this whole domain, we have some substances which are transported by advection in the fluid part and by diffusion, and in the solid part just by diffusion. So we have, let's say, we have two solutes, but you could have also two vectors of solutes. So we have C epsilon F, and we have, this is the solute concentration in the fluid, and on the other slide we have C epsilon S, which is the solute concentration in the solid. And in the fluid part, so you see omega epsilon F, this means in the whole fluid part, in the bulks and in the fluid part of the membrane, we have this transport equation. So we have a diffusive transport and we have an advective transport by the velocity V epsilon, which I described before. This is in the bulk domains. Then we have in the membrane, again, a transport equation, which is scaled. You see here we have 1 over epsilon in front of the time derivative and epsilon to the power gamma in the diffusion. No, sorry. Here, the equation for the solid concentration C epsilon S is already here. So yeah, so okay. So this is the equation in the fluid part. Then we have the equation in the solid part, which is now scaled, as I said, and we let gamma free. Gamma is a parameter which is in the interval -1, 1. And now we need for the concentration C epsilon F, we need some conditions at the outer boundary. Yes, so at the lateral boundary we again impose periodicity. At the upper boundary, which we denote Dn omega, we have again this Neumann boundary condition, so zero flux. And then we have to say what happens with the concentrations at the interface gamma epsilon between the blue domain and the white domain. Yes, the solid domain and the fluid domain. And there we say that the flux of substances is continuous and is given as a function of the concentration. This is a nonlinear function of the concentrations, and this nonlinear function you can imagine as reactions which take place at this interface, yes, involving these two species. Okay, then we have initial conditions for all concentrations, and that's it. Okay, now let us make some reminders. So this system is the Stokes system is decoupled from the transport system. In the transport system, we have the velocity entering the transport term here for the concentration. Yeah, so we have a partial coupling, so the Stokes system lives for itself, but it is coupled to the transport equation by this advective term, which appears here. And we have then between the two solid and the fluid part, the concentrations, of course, are coupled here through this nonlinear term on the interface gamma epsilon. Okay, now this is the only more full slide, but let's go through. I just want to show you the weak formulation. So we are considering weak solutions for our model, and so we write a weak formulation. So what will we have? We will have an equation for the fluid velocity and the pressure, which will consist of these parts V epsilon plus and minus and V epsilon m. Yes, so this is the weak formulation of the Stokes problem in the bulks and in the membrane fluid part of the membrane. Then we have a weak formulation for the solute in the fluid part. And what I want to emphasize here is that now we have this boundary term on our interface gamma epsilon between the fluid and the solid, which is this nonlinear term. And then we have again this lives on omega epsilon f. And then we have the weak equation for the solute from concentration of solute in the solid part, where we have again this term as a source term living on the interface, and this equation was formulated on the blue part of our microscopic domain, yes, on the solid part. Now, why do I write this? Why did I wanted to show you this? Because now our aim is to let epsilon go into 0 and to pass to the limit in these equations for the velocity, for the pressure, and for the concentrations CF and CS. Yeah? Now, which are the bad terms? What would you say? Excuse me? The bad terms which cause difficulties when passing to the limit. Let's search for ugly terms. So, I mean, nonlinear terms are ugly, yeah, because then we need strong convergence instead of weak convergence. So where do we have nonlinear terms? We have these nonlinear terms, which are especially ugly because they also live on this interface gamma epsilon, which is oscillating or which is varying with epsilon. Yeah. Then we have the advective term in the transport equation in the fluid part, which is also a nonlinear term. Okay, and then we always when we have time derivative and you want to pass to a limit and you don't have enough regularity, also is not so nice. Okay, these are the terms which we have to work a bit more in order to get the convergence in the limit. Okay. Now, do you have questions for this weak formulation? Because, or for the whole system which I presented until now? It should not be too complicated. We have the fluid part, which is everything outside of this blue part. Then we have the concentration which lives in the fluid part, and we have the concentration which lives in the solid part. These are the three components. Okay, now, as I said, what is the problem with this system? The problem is that due to this periodic structure, microscopic structure, this is very complicated. If you want to do numerical computations, then this periodicity is very, very small. So you have a high complexity. So you want to reduce the complexity. So what do? We say we let epsilon going to 0. But when we let epsilon going to 0, what happens here is first this membrane having height 2 epsilon will shrink to an interface, okay? And then, of course, we have to see when we pass with epsilon to 0, all these functions which live in the membrane, they see some periodic structure, and we have to have special methods to deal with such periodic, when we pass to a limit in such functions defined on such a microscopic geometry. So these are the two-scale methods. Okay, now I put a slide to discuss a bit what challenges do we encounter when we pass to the limit. So as I said, first we have to deal with this microstructure, and second we have to deal with this dimension reduction, because from a three-dimensional domain, which was the membrane, until in the epsilon model, we will shrink to an n-1, so a two-dimensional domain, so an interface, and so we have to deal with this topology change of our domain. And okay, so let me enumerate a bit, and then I go into and then some of these parts I will describe more precise. Okay, so we have, in order to pass to the limit, we want to have some to rely on some compactness results. So we have to have some estimates and then get some convergence sequences or subsequences at least. So we have to estimate all our quantities. What causes problems is first the pressure in the porous layer, because when estimating the pressure, one possibility is to work with Bogovsky operator, but now we have some functions which are coupled in the membrane, which are coupled to the bulk domains, and this causes some difficulties when we construct this Bogovsky operator due to this coupling to the bulk. Then, since we saw that we have nonlinear terms, we have to show estimates which allow to get strong convergence, and also, of course, we have to estimate convective terms in the convective term in the porous layer and the nonlinear term of gamma epsilon. And when we estimate this term, we had to derive or to show some new embedding results in the layer and some so scaled. What is the new here? So the scaling is important. You have to control this epsilon in your embedding constants. Yes. And also trace inequalities on gamma epsilon. Since this interface is depending on epsilon, you have to take very good care in your trace estimates in your constants. What is the dependence on epsilon? Okay. Then, of course, as I said, we want to derive strong to scale compactness results. So finally, we will show that the traces converge strongly in two scales. I will come in a moment on this. So here we use some Kolmogorov-Simon type arguments. Then, as I said, we have to show to have good converge concept to pass to the limit in the time derivative. And here we tried to formalize this concept which we developed just in terms of formulating a priori estimates, and then from there following then this convergence results. And last not least, when you want to pass to the limit, then one important, so especially when we want to derive the interface law on this interface which we obtain in the limit, then you know, maybe a very crucial point is to have the good test functions. Yes, test functions which are adapted to the structure of your solution, and therefore we constructed a space where you see we have our final solution. How will it look like? So we have a solution which so our limit will have a part which lives on omega plus, part which lives on omega minus, and then some part which has to take care somehow on the standard cell. So we should not forget what happens in the layer, and this we capture in the standard cell, which is then the third part of our limit. Okay. And so we find suitable set for the test functions, such that we can then, using this test function, get our effective laws. Okay, now let me give you some of these results which we use and try to point out what is the point. Yes. So now here you see we have an estimate which we have the LP norm in this omega epsilon MF. This is the fluid part in the layer. We have the LP norm, and we estimate it by the gradient in the layer. And we have some part. What is this G epsilon? This G epsilon, this G is a part of the boundary of the standards of the ZF, which is the so as I said, we have here the our cell. So we have here this ZF so this is the solid part. Yeah, and this is the ZF. Outside of the solid part, this is the ZS. This is this solid part, and this interface between these two phases, this interface, this we call gamma in the cell, in the standard cells. Yes, and so if we take some part of the boundary of the ZF, then this generates a G epsilon, which is a part of the boundary of our thin structure. And so we estimate the LP norm in this fluid part of the layer by the gradient, which is scaled accordingly, and by the L2 norm of on the boundary of part of the boundary of this layer. Okay, now when we take, for example, this G to be the S plus and S minus, so this ZF has boundary also this S plus and S minus. Yes, if you take this, then this we have this. So if you go from there to there, and we take P equal to 2, what happens? We have the L2 norm in the fluid part of the membrane. Then this is estimated by square root of epsilon. So inserting here P equal to 2, this vanishes. So we have square root of epsilon times the gradient in the fluid part, and plus the L2 norm of this whole surface S epsilon plus and S epsilon minus. And if we now estimate this by the bulk domains, then we get here an estimate where here we have just the H1 norm on the whole on the full domain omega epsilon F, and especially this estimate was derived by Konka in 1985, and this turns out to be a special case of our more general embedding estimate. And just one more for the trace, we also managed to estimate a trace on gamma epsilon by some part which comes from the gradient scaled with square root of epsilon. So this is, we try to keep this contribution from the gradient in the fluid part of the membrane small. And then we have a part phi epsilon in the bulks and the gradient in the bulks. Yes, so this is. And if we can infer from there, for example, that we can estimate the boundary L2 norm on this oscillating boundary by the H1 norm or H beta norm in the whole fluid part. And since we can estimate this from the a priori estimates, these two norms, then we get some estimate for the trace. Yeah, this is important to get then compactness results. Okay, now here are the a priori estimates. So what is interesting here? Interesting here in the bulk domains omega plus and omega minus, nothing is interesting. You have the L2 norm of the time derivative of the velocity, the H1 norm of the velocity, and the L2 norm of the pressure. This is what you know from Stokes. Here in the membrane, you have some scaling. So the L2 norm is scaled with 1 over epsilon. The gradient is scaled with square root of epsilon. The pressure is scaled with 1 over epsilon. Yeah. Okay, then what about the concentrations? So this is the C epsilon F. This is a concentration in the fluid. Now this is a transport equation with advective term. Yes. So what do we have? We have the time derivative is in the dual space of H1 omega epsilon F. Then we have the concentration in L infinity L2 and the gradient of the concentration L2. So also what you know from parabolic setting. And for the concentration in the blue part of the microscopic domain, we have this scaled estimates, and at the scaling, which is here you see in front of the gradient, this will be decisive for the limit equations which we get. Because why? Now you see here we have epsilon to power gamma over 2 times the gradient is less or equal C. Now if we see if this is a big term. Yes, so that means if gamma is negative, if gamma is -1, yes, then we have 1 over square root of epsilon, and then you bring it to the other part is a small term, then that means the gradient is small. Therefore, we say for gamma equal to -1, we have small diffusion. For gamma equal to 1, this is a small term. If you bring it to the other side, the gradient will be big. So we'll have So if gamma is 1, then we have here epsilon to the square root of epsilon, and then that means that the gradient. So this is the situation of the small diffusion. Okay, this we see better from our scaling in the equations. Yes, so we have here. When gamma is -1, this diffusion coefficient is very big, yeah, because we have 1 over epsilon. If gamma is 1, we have a small diffusion coefficient, and if gamma is between -1 and 1, we say we have a moderate diffusion, and we will see in the limit what this implies. Okay, now why have I put this in red? I put this in red because this is not good enough for our compactness results. Why? Because we like in the layer estimates of this kind, where the L2 norm is multiplied with 1 over epsilon, and this is bounded. Why this? Okay, now imagine we have bounded just the norm as it is here. We take the part of the layer. And just this is bounded in the layer. Then, for example, if V epsilon is a constant, yeah, then the layer has thickness 2 epsilon, and in the limit, so this will be something of order epsilon. this norm or square root of epsilon, and in the limit, if I don't have this, so this will be of square root of epsilon. If I don't have this factor here, this would go to 0, because if V epsilon m is a constant, then this norm is of order square root of epsilon and would go to 0. Yeah, so this factor here is important, and indeed, if we work a little bit more, then we get also for the fluid concentration here in the fluid domain, we get this estimate with the 1 over epsilon. Yeah, and this we get by using our improved embedding estimates and trace estimates. Okay, now what we use as a convergence, now we want to pass to the limit, yes, of course we could in the bulk domains we just test with smooth functions. Yeah, this is weak convergence, which what we expect there and what we use there. But in the membrane, we want somehow to get out from our solutions, from our microscopic solution, this oscillatory properties. Yes, and this we figure out by taking test functions which oscillate themselves. Yes, and even then in the solution is also an oscillation. Then these test functions figure out oscillation which you have in the solution. So testing with such oscillating test functions, you get a limit, and in this limit pops up a new variable. This is the variable u, which lives in the standard cell and which tells you, okay, now with respect to this variable, I described oscillatory properties of your microscopic solution, which you don't see here. Yeah. Okay, and this is called to scale convergence. So we say W epsilon converges to W 0 of t, x bar, and y. If this holds, if this equality holds, and now, okay, so what do we have here in comparison to here? Here, this x lives in the three-dimensional layer. Yeah, this is clear because my layer for given epsilon is three-dimensional. But here, this x bar is just the tangential components of the first two components of the x. Yeah, because in the limit, we don't see the layer. We just see the standard cell that we see from this convergence, and we see the interface sigma. So our limit will depend on x bar and maybe also on this y if it depends. Sometimes this depends also on y, sometimes it is independent on y. Yeah.
There should be phi in the
Yeah, this should be phi, of course, this should be phi, that's clear. Yeah, thank you. Okay, and then also here we have a strong convergence, a strong to scale convergence, and the strong to scale convergence is if the norm scaled by 1 over epsilon or square root of epsilon converges of W epsilon converges to the norm of V0 again, of course, in the suitable space where this limit lives. Yes, so we have to take. You see, this is not like in the standard strong convergence in L2 or yeah. So what do we know? So this is a bit more special, this to scale convergence, but it is the method which helps us to extract from our solutions, microscopic solutions V epsilon, the oscillatory properties. Okay, and now this is the same thing we can do for functions which are defined on gamma epsilon. Yeah, this is the surface of this blue structure, and then our y will live on the surface gamma and not on the whole standard cells. And the strong, we have also here a strong convergence. Now this is important because now I will formulate a lot of convergence results, and some of them are related to this two-scale convergence. Okay, now with respect to this two-scale convergence, we have compactness results which says, okay, if I have suitable bounds on the microscopic solutions, then there exists two-scale convergence subsequences. Yes, so this we can show for the solution itself, for the gradient of solution, and so on. This I have no time to describe here, but this convergence type makes sense because of this compactness results which we have with respect to this solution, to this concept of convergence. Okay, now let me tell you a bit about, so I have time until somehow 35 or 40 or something like that? Okay, good. Okay, maybe I don't need so much, but I know I have time. So now let's look at the velocity. So the velocity V epsilon plus, V epsilon minus, and V epsilon m. What do we expect? In the bulk domains, we expect that nothing happens. Yes? So the velocity converges to a limit. Now, what do? We take the velocity in this omega epsilon plus and minus and multiply by the characteristic function of omega epsilon plus minus. So then this also is a function which lives on whole omega plus. And then we have this strong convergence to a limit which lives on omega plus. The same for minus. Then we have the V convergence of the gradients. This is now based on our a priori estimates, yes. We have the V convergence of the time derivative, and we have the convergence of the pressure. So in the bulk domains, does not happen very much, but they are important because we always have this coupling, and which is there. We cannot, we have to take into account. Okay, now more interesting is what happens with the velocity V epsilon m in the layer. And this velocity now now converges in this two-scale sense. You see here, we had just normal convergence in the domains omega plus and omega minus. Now we have this two-scale convergence, and we have that the velocity convergence in two scales weakly. Epsilon times the gradient converges in two scale to the gradient with respect to y of this limit V0 m. The pressure converges to zero, the time derivative converges to zero in two scales, and the pressure converges to zero in two scales. Now, for people who are acquainted with this homogenization of the Stokes, you will remark that this is a special kind of convergence, because usually here we have the convergence to the Darcy pressure. Now here the Darcy pressure is zero in this case, because of this thin layer. Because of the scaling in our equation, because we have also thin layer case where we get a Darcy law with the Darcy pressure different of zero. So Marcus has some work in this, for example, in this for such models. But the scaling which we have here in our equation gives us this convergence of the pressure. And then we have from the convergence, from the passing to the limit, we already have some coupling between the limit in the bulks and the limit in the layer. So the limit in the layer, this V0m, you see from here, this is a function which lives on 0t times x bar on sigma and on the standard cell. So we have this y. And now, if you say this on S plus and S minus, these are these two parts of the cell. If you say that our limit function is equal to V0 plus minus, that means on this part of the cell, this does not depend on y, yes, because V0 plus and V0 minus don't depend on y. And also we have for the limits in omega plus and omega minus, for these limits here, we can show that the third component is continuous. Yes, so this we also get by just passing to the limit. So from the equations. Okay, in the for the convergence of the solute concentration in the fluid, we get again convergence. I think I will skip here what is, or just say what is important. So we have this strong convergence of the, what is this tilde? This tilde is the extension. We extend the solution from the fluid part to the whole domain omega. Then we can say something about this extension, and this extension converges strongly to a limit which in H beta. And this helps a lot when we want to show the compactness, the strong compactness on the boundary gamma epsilon for this concentration. And if we go then to the convergence of the solute concentrations, we have, depending on gamma, we have different type of convergence. and different type of limits. So I just want to emphasize that now here, when we have the high diffusion, huge diffusion, then the limit of the solute in the blue part in the solid domain will not depend on y. It depends just on sigma, on x bar. Yes. If we have gamma between -1 and 1, this is the case of moderate diffusion, then the limit again depends just on sigma and not on y. And in the limit for gamma equal to 1, we have a C0s, which now is depending on s bar, on x bar, so lives on sigma, and depends also on the variable which lives in the cell, and namely in this standard cross here. Okay, and now maybe the most interesting part of the talk. What do we get in the limit? So in the limit, we have two compartments which are separated by an interface. Now, for the fluid flow, we get Stokes in the bulk domains, and we get some transmission conditions at the interface law at this separating interface. Now, what we formulated here is we have now the jump. So this we have the normal stress, and from the normal stress from V plus and V0 minus, we take first the normal components and take the jump, and this law says that the jump in the normal component is given by a law which depends on V0 plus and V0 minus. And then we take the tangential component of the normal stresses for V0 plus and for V0 minus. And here again, we get that this tangential component is somehow depending on the trace V0 plus, but also the trace V0 minus. And to comment a bit, so this reminds us to the so-called Beavers-Joseph law, yes, where you have that the tangential component of the normal stress is coupled to the value of the velocity at the interface. Okay, and now you see here coefficients. From where do we get these coefficients? These are exactly coefficients which take into account the structure of our medium. So this is a cell problem which lives on the standard cell ZF, on the fluid part of the standard cell. Okay, then we have for the fluid part, we have what? We have in the whole domain, we have a transport problem. How does now the microstructure influence this transport problem in the fluid part? By this source term, which is a singular term, which lives just on the interface sigma, and which is computed as integrals over the so this is a functional which is computed from the limit of the reaction term of the nonlinear reaction term H. Yeah, so the rest is as we had it in the microscopic equation. The contribution of the microscopic structure is through this singular term on the interface gamma, and this comes because of the reaction which are taking place at this interface. And for the solid phase, now our effective equations depend very strongly on the values of these parameters gamma. If we have high diffusion, then fast diffusion, then we obtain here a diffusion equation which has so-called homogenized diffusion tensor, which is not, of course, lives on sigma. Yes, so this is a 2x2 tensor. Then, and in the right-hand side, we have a source term, which again comes from these reactions which take place on sigma epsilon. Then we have the moderate diffusion. We have, in the case of moderate diffusion in the epsilon problem, the diffusion in the limit, the diffusion operator vanishes. We have just an ODE here. for our limit concentration. Again, the source term is given by this reaction term. And if we have slow diffusion, then we have a solution. So our limit solution is actually a cell solution which lives on the standard cell, and which depends. So we have a solution in this standard cell here on this cross, and for each x bar in sigma. In each x bar in sigma, you have to see we attach, so this sigma, we attach such a problem which lives on the standard cross. And also here we have that this reaction are the right-hand side of a flux of our Neumann boundary condition. Okay, so you see we have here three types of equations, macroscopic equation for each situation of our parameter gamma. Okay, and I think that's all. So what did we do? So we showed this homogenization of this complicated and coupled problem of Stokes and transport in this thin membrane with a microscopic structure. And the important part here, also an important aspect, is that we have a flow through this membrane. So in former models, this was the first time when one manages by homogenization to get a flow through. So we also had a model which with another scale which is considered before, and there there was no flux of fluid through the interface. Yeah? So this is the right scaling to generate such a flux, and this is important for applications. And to give a short outlook is, of course, you can look at this structure, at the solid structure as a elastic structure. Then you have to add to this system the elasticity equation for the solid part. And this is an ongoing work, and so actually it is more or less solved, and this case should also work. And to give you an outlook for tomorrow, so with such a homogenization problem where the elastic properties come in, tomorrow Markus will give a talk which also considers such elastic problems of the microscopic solid part. Okay, so thank you for your attention, and I'm here for questions.